Hello, everyone. Today, I want to talk about two important metrics in classification, the recall and the precision. But more specifically, I want to illustrate the trade-off between them. And then I want to introduce the F1 score, another very well-known classification metric, as a metric that we can use to balance that trade-off. My goals with this video are to explain briefly what recall and precision are, then illustrate the trade-off between them, and then finally introduce the F1 score as a metric that allows us to balance that trade-off. Okay, first, I'm going to start by importing the functions and libraries that I'm going to use in this video, and that's what these two called cells do. Just do that, import everything. Good. Now let's go ahead and load the data set. The data set is the default data set. Um, I have that data set stored as a CSV file locally in my computer, and I already uploaded that CSV file right here to the Files tab in Colab, and that allows me to use the path to that CSV file in Colab to read it as a data frame. So I'm going to be able to read that CSV file as a data frame by using the read underscore CSV function from pandas, okay? And I'm going to create that data frame with that CSV file, default DF, okay? Let's take a look at that data frame. This is actually a simulated data set. So it simulates data about 10,000 people. And for each person, we have information about whether the person defaulted or not in her credit card balance, um, whether the person is a student or not, the person's credit card balance, and the person's income. The target variable here is default. So remember, we're going to talk about classification. So, and the target is default, and that target is categorical. So that column takes two possible values, yes or no. Yes means the person defaulted. No means the person did not default in her credit card balance. Okay, so we have this categorical target and three features, student, balance, and income. Okay. So let's do a brief data exploration and preparation. In terms of data exploration, one thing I want to do is, I want to see the class distribution. So how many observations belong to the positive class, how many observations belong to a negative class. And in this case, we can see that let's round to 97. So 97% of the observations belong to the no class or the negative class, and 3% belongs to the positive class. Okay. Okay, so this is an unbalanced data set, as you can see, because the negative class is much more frequent than the positive one, okay? One thing I want to do, and this is totally optional, guys, what I'm doing right here is totally optional, but in scikit-learn, it's okay to work with character classes, right? So the classes are no and yes, so they are character values, right? It's totally fine to work with them in scikit-learn. In other machine learning apps, we must work with numeric classes. So we must work with zeros and ones instead of nulls and yes, okay? So that's why, kind of to be consistent with other machine learning applications, I transform the no into a zero and the yes into a one, okay? We don't have to do that in scikit-learn, but again, to be consistent with other applications, I did it. And sure enough, I did that transformation. And now when we take a look at the default column again, now we don't see no and yes, we see zero and one. Okay. Okay, so our classes will be zero and one. Good. Another transformation I want to do is for this column, that column, which is a feature, right? Student is one of the features. That column has object data type. That means it's categorical. And remember, in machine learning, when you have categorical features, you must transform them into numeric. And you can do that transformation using one-hot encoding or dummy coding. In this case, I apply dummy coding and I transform um, the student column into a dummy column, okay, by using the get dummies function from pandas, okay. And I created a new data frame with that dummy. So default df dummies, that's the kind of final data frame I'm going to be using in this video, okay. Let's take a look at that data frame. Very similar to the original data frame, default df. We still have default column, the target, balance, income, but we don't have the original student anymore. We have student yes. And a student yes, notice that it's Boolean. So takes true when the person is a student and false when the person is not a student. It's okay to work with Booleans. because internally Booleans are treated as numeric. So the false is treated as a 0 and the true is treated as a 1. Okay, so this is good. So all the uh, features are in the correct format now. Okay, the last pre-processing step we need to do is we need to split the data into training and testing. Remember, in machine learning, when you're training an algorithm, you need to train that algorithm with the training data, and then you need to leave the test data to evaluate the performance of the algorithm. Okay, so we always need to split the data. And in other videos in my channel, I have explained how to split the data in scikit-learn. So I have explained this function, train, test, split, in many other videos. So I'm not going to do that again here. Okay, so I'm just going to run these three code cells. But definitely, when you run these three code cells, the data will be split into 80% for training and 20% for testing. Again, I have explained these three code cells many times before. Okay, so after that, we are ready to apply our machine learning algorithm. And remember, we're talking about classification, so we need to apply classification algorithm. Why? Because the target is categorical. And the machine learning algorithm I'm going to apply is logistic regression, okay? As I said here, I used all the default hyperparameters from the logistic regression algorithm available in scikit-learn. Okay, so I just the default ones. Now, if you're interested in knowing what are the different hyperparameters for the logistic regression function in scikit-learn, how to change them, you can do a Google search, scikit-learn logistic regression, and then the scikit-learn documentation will pop up. Okay, and you can explore it. Okay. Here, what I'm doing, guys, is I am actually defining the model with that code cell, okay? And notice that I define the model by using the make pipeline function. Why? Why am I using this function to define the model? Because that function allows me to specify that I want to standardize the features before applying logistic regression, okay? That's a requirement. When you apply logistic regression, you must standardize the features first, and that function allows me to do those steps in a sequence. So standardize, then apply the specific machine learning algorithm, which in this case is logistic regression. Okay. All right, so let's define the model, which I title logistic regression model. And now in the next code cell, I train the model by invoking the fit function on the training data. Perfect. So model train very quickly. Now what I'm going to do, as I'm saying right here, I'm going to use the model, the train model, to predict the test data and then later evaluate its performance. So once we have the predictions on the test data, then we can compute the recall, the precision, and then illustrate the trade-off between them. Okay, but we need to have predicted data in order to compute performance metrics, right? So that's why we need to use the model to predict the test data. And that's what I'm doing here. Calling the model, then invoking the predict method on that model, and then passing the test data, okay? And one thing that I want to mention here, guys, is that in scikit-learn, when you invoke the predict method, a threshold of 0.5 is used to come up with a prediction. So let me repeat that. When you invoke the predict method in scikit-learn, a threshold of 0.5 is used. What is the threshold of 0.5? Remember, guys, take you to this slide. In any classification setting, this is what happens when it comes to making predictions. So that inequality right there, that inequality is evaluated for each observation to be predicted. So if the predicted probability returned by the model is greater than 0.5, then the observation will be predicted to have class 1. Otherwise, it will be predicted to have class 0. Okay? So in that inequality, we have two things, right? The predicted probability returned by the model. And that is something that you don't see that predicted probability here, but whenever predict is invoked, for each test observation to predict, that predicted probability is returned, okay? So if that predicted probability, that again, we don't see, but it is there, if that predicted probability is greater than 0.5, we predict 1. This 0.5 is the probability threshold, okay? And again, in the background, when you invoke that method, that inequality is being evaluated for each test observation to be predicted. And again, that is the probability threshold, and that is something that we can change. So we can change that default value of 0.5, and that's what I'm going to do later. I'm going to change it, and you will see what happens with precision and recall. Okay. Okay, so now that, let me run this. Now that we have the predictions of the test data for the target stored right there, let's compute precision and recall, okay? And then let's understand what they are. Before computing precision and recall, I'm going to print the confusion matrix, which remember the confusion matrix is simply a matrix that shows the actual and the predicted results for both classes, okay? Okay, that's a confusion matrix. And how do we interpret that confusion matrix? Well, what are these numbers? So that 1,924 is the number of true negatives. So that's the number of actual negatives correctly predicted as negatives. Okay. How about this 9? That 9 is the number of false positives. So that's the number of actual negatives incorrectly predicted as positives. This 43 would be the total of or the number of false negatives. So that's the number of actual positives incorrectly predicted as negatives. Okay. And finally, that 24 would be the total or number of true positives. So it's the number of actual positives correctly predicted as positive. Okay. Knowing that, we can go ahead and compute recall and precision. But first, I guess we need to define what recall and precision are, right? So let's define what recall is, and then let's use that definition to compute recall. Recall, guys, is the proportion of actual positive observations that the model correctly classifies as positive. So let's use that definition to compute recall, okay? So proportion of actual positive observations that the model correctly classifies as positive. So let's get the total number of actual positive observations, right? What is the total number of actual positive observations? And that will be the bottom of the recall calculation. Total number of actual positive observations. 43 plus 24. Let me type it and then I'll explain you. 43 plus 24, because that's the number of false negative and true positive, okay? All of those are observation that are actually positive, right? So both the false negatives and the true positives are actually positive observations, okay? So it's the total number of actual positive observations. And then how many of these observations the classifier correctly identifies as positive? The number of true positives, 24, okay? So that's why we get a recall of 0.358. So like as a percentage will be 35.8. So let's round it to 36 for the sake of a simpler interpretation. So let's say 36% recall, right? So a 36% recall is very low, right? Why? Because 36% is telling us that among all the observations, okay, um, the observations that belong to the positive class, right? So among all the actual observations that belong to a positive class that the model encounters, it only correctly identifies 36% of them. So it misses 64% of the actual positive observations that the model encounters. It's very, very low recall, guys, okay? Okay, so let's compute the precision. And again, let's first define precision, and then let's try to compute it. So what's precision, guys? Precision is the proportion of the total number of positive observations predicted by the model that are actually positive. So proportion of the total number of positive observations predicted by the model. So don't get confused. Recall was the total number of actual positive observations, right? Total number of actual positive observations that are actually correctly identified as positive. But here we're talking about total number of positive observations predicted by the model, okay? And among those, how many are actually positive, okay? So let's use that definition to compute the precision. Let's get the total number of positive observations predicted by the model, and that will be the bottom of the precision computation. So total number of observations predicted by the model, right? Total number of positive observations predicted by the model. Well, that would be 9 plus 24, right? Be 9 plus 24. Let me type it and then I explain. So 9 plus 24. Sorry, 9 plus 24. Why? Because that is the number of false positive plus true positive. Both false positive and true positive are observation predicted as positive, right? False positive, true positive. So Both are observations predicted as positive. So that's why when we add false positive plus true positive, we get the total number of positive observations predicted by the model. How many of these observations are actually positive? True positive, the number of true positive, 24. Okay. And we get a precision of 0.727. 0.727. If we transform that into a percentage, it would be 72.7 rounded to 73. So let's say 73. Okay. So a 73 precision is telling us that, when the model predicts an observation as positive, 73% of the times this prediction is correct. All right. So the way I like to think about precision is in terms of trust. Like precision is about how much we can trust the model when it predicts an observation to be one. I guess with a precision of 73, we can say that we can trust it somewhat, but not a lot. Like when the model predicts an observation as one, we can trust the model somewhat, but not a lot. Okay. So 73 precision is not low necessarily, but it's not high either. It's not super high either. So definitely it's not as low as Rico's 36%, but it's not high either. Okay. Um, okay, so now we know what precision and recall are, how to compute them, and I just want to show you that actually to compute precision and recall in scikit-learn, you don't need to do it like this, semi-manually from the computation matrix. There are built-in functions, guys. There are built-in functions in scikit-learn to compute precision and recall. So to compute recall, we can use that built-in function, recall score, and to compute precision, we can use that built-in function. Okay, and sure enough, we get the same values. Okay, so recall, same what we got. Okay. And precision, same what we got, all right? And I also printed the overall accuracy just for give you an extra information, okay? All right, so now you know how to compute precision and recall in scikit-learn, but not only that, you know what they mean, okay? Knowing that, let's go ahead and illustrate the trade-off between them, all right? So let's illustrate the trade-off, but actually before illustrating the trade-off, let's define the trade-off with words, okay? So this is the trade-off defined. So for any given classification algorithm, and what do I mean by that? Any given classification algorithm. That means that if you want to understand the trade-off, you need to focus on using one specific algorithm. Okay, so you cannot be using different algorithms. So given one algorithm, um, for any new configuration we try with that algorithm, we will observe that as either recall or precision improves, the other one worsens. Okay. Now, here, guys, I'm talking about using one algorithm and trying new configurations with that algorithm. Okay. So in this specific problem, what new configurations should we try with logistic regression? Well, this is an unbalanced data set, isn't it? Remember, 97% negative class, 3% positive class. So with an unbalanced data set like this one, to focus the performance, not only on the overall accuracy, okay, but also on the precision and the recall, a very common configuration that we should change is the probability threshold. Okay. And remember that that's that's a well-known thing to do when you have an unbalanced data set. When you have an unbalanced data set, you can not only focus on the overall accuracy. I'm not going to explain why, the reasons for that in this video, but yeah, with an unbalanced data set, you cannot focus the performance on the overall accuracy. You need to focus the performance on class-specific metrics like the precision and recall. Okay, so with unbalanced data set, if you want to improve precision and recall, very commonly what you should do is change the probability threshold. And that's what I'm going to do now, guys. I'm going to change the probability threshold, okay, uh, to illustrate that trade-off, okay? And again, changing the probability threshold, it's a common new configuration to try when you have unbalanced data set and you want to improve precision and recall, okay? All right, so guys, I already have a video on my channel explaining all the details about how to change the probability threshold in scikit-learn. That video is titled Changing the Probability Threshold for Unbalanced Data. In that video, I explain all the details of the Python code needed to try different thresholds. So for the sake of saving time, I'm not going to explain in this video the code for how to change the probability threshold. Okay. So if you want to understand the code that I'm about to use to change the probability threshold, which is actually like three or four lines of code, but if you want to understand it, please watch that video. Okay. All right, so let's go ahead and change the probability threshold. What I want to do is actually I want to first reduce the probability threshold to a value below 0.5, okay? And then increase it. So use a value above 0.5 and then see what happens with precision and recall, okay? So let's change the probability threshold. And to do that, we need to invoke the predict proba method on the model. And from that, we need to retrieve the second column only, which is the probability that the target equals 1. Okay, so that's the probability that the target equals 1. And then we use those predicted probabilities. Okay, that would be the predicted probabilities. This numbers right here. And we use those predicted probabilities to get predictions for new thresholds. Okay, so let's get the threshold. Sorry, let's get the precision on recall for threshold 0.3. So let's change the threshold to 0.3. Let's see what happens with precision on recall. Okay, these are the predictions with that new threshold, 0.3. So we are reducing the threshold now. And let's see what happens with recall when we reduce the threshold. So recall originally with 0.5 was 0.358. With threshold 0.3, it went up 52%. So it improved. Okay. How about precision? Well, precision with threshold 0.5 was 0.727. Now with threshold 0.3, it went down. It worsened. So it reduced to 55%. Okay. All right. So what happens if instead of reducing the threshold, we try to increase it? Okay. So we go the other direction. So if we increase it to 0.7. Okay. Well, let's get the predictions with 0.7 right there. And let's see what happens with recall. So recall with 0.5 was 0.358. Now with threshold 0.7 is 0.269. So the recall reduced. It worsened after increasing the threshold. How about precision? Well, precision with 0.5 was 72%. Now with threshold 0.7 is 90%. So it improved. Okay. Well, guys, I just illustrated the trade-off. I illustrated that, when you reduce the threshold, okay, the recall improved, right? But the precision worsened. But in contrast, increasing the threshold hurt the recall, but improved the precision. That is the trade-off. Like when you move the threshold in one direction, one improved and the other worsens. But when you move the threshold in the opposite direction, the opposite happens. So that's the trade-off. When you reduce the threshold, recall improves, precision worsens. But when you increase the threshold, recall worsens and precision improves. Okay. Now I'm gonna do a chart. I'm gonna do a chart now illustrating that trade-off in a clearer way, because in this chart we're gonna be able to see the values of precision and recall not only for two thresholds but for many different thresholds. Okay, so let's go ahead and do that chart. Okay, before doing the chart, I actually wrote that function. Okay, so let me run that code cell. And that function is just to facilitate the calculations that I need to get the chart done. This is just a function that given a threshold will give me the predictions for that threshold. Okay. All right. So using that function, we can loop through many different thresholds and get the following chart. And what do we see here, guys? So we see on the x-axis, we see many different thresholds, right? And on the y-axis, we see the performance metrics, and the performance metrics are the green dots would be the recall, and the orange dots would be the precision. What do we see here? The pattern is very clear, right? As the threshold increases, the recall tanks, so the recall worsens. And as the threshold increases, the precision improves. It goes up, okay? Or the other way around, like if you go from right to left, as the threshold decreases, the recall improves. And when you go from right to left, as the threshold decreases, the precision worsens. So it goes down, all right? So that's the trade-off, guys. So we see that if we move the threshold in one direction, like we see two different behaviors in terms of precision and recall. One's improved, but the other one worsens. Okay. Guess what? One idea to navigate the trade-off is to use the arithmetic mean between precision and recall to choose a kind of good threshold. Okay, because actually we have a quandary now. Like given this opposite patterns, right? What do we do? What is a good threshold to use? So it's kind of hard to select, right? So one idea is why don't we get the arithmetic mean between precision and recall, and we use the arithmetic mean to make that decision, okay? So what I'm going to do now is I'm going to repeat that same plot, but showing the arithmetic mean in addition to precision and recall, okay? Let's go ahead and do that. There you have it, same chart, but now those red crosses will be the arithmetic mean between precision and recall. Um, guess what, guys? The arithmetic mean is actually a very bad metric for selecting a good threshold. Why? Why am I saying that? Notice that the highest mean happens right there. And that happens for threshold 0.7, right? So the highest mean happens for threshold 0.7. So according to the mean, to the arithmetic mean, the best threshold, right, is 0.7, right? Guess what? 0.7 is a very bad option. Why? Because it results in a very, very low recall. Okay. So for 0.7, the recall is below 30%. So 0.7 threshold, recall below 30%. So guys, there is no way on earth that a good classification solution give us a recall below 30%, okay? So that's one issue. That's one of the issues with attempting to use the arithmetic mean to navigate the trade-off, okay? In situations where one of the values is high, but the other one is low, the arithmetic mean, unfortunately, favors the high value, and it leads us to select bad options like this one, okay? So this is what we need. We need a metric that, let's say, weights more strongly on very low values of either recall and precision. That's what we need. We need a metric that with a recall like this so low, it doesn't tell us that is a good option. Okay, that's what I'm saying. Like we need a metric that weighs more strongly on very low values for either recall or precision. Okay, because a very low value for either recall or precision means that threshold is not a good option. That metric, guys, is the F1 score. Okay, the F1 score is a metric that can give us that. One interesting thing about the F1 score is that the F1 score is actually an average also between recall and precision, but it's not the arithmetic average. It is the harmonic average, okay? And when we're dealing with fractions like precision and recall, one advantage of the harmonic mean over the arithmetic mean is that, let's say, it gives us more protection against extreme values from either precision or recall, okay? So the arithmetic mean gets more, let's say, distorted by a large value of either recall or precision than the harmonic mean. So that's why, as you will see, the F1 score is a better summarizing metric, okay? So why don't we repeat this plot, but now uh, showing the F1 score for different thresholds and see how to interpret it, okay? Let's do that, okay? So let's get the same plot, but showing the F1 score for the different thresholds. And as I'm saying here, guys, when navigating the trade-off between recall and precision, the F1 score could be used as a very good, actually, summarizing and balancing metric. Okay, so let's get that plot, but now showing the F1 score for the different thresholds. Okay, that is the plot. Okay, and again, this is just on the x-axis, different thresholds, and on the y-axis we have the F1 score for each threshold. Okay. What do we see here, guys? Well, the first thing I want to point out is that remember that threshold 0.7 was the best one according to the arithmetic mean? Well, according to the F1 score, threshold 0.7 gives us the second lowest value, so the second worst value, because obviously for the F1 score, as for the other metrics, the higher the value, the better. So we want high values, right? So 0.7 gives us the second lowest, the second worst value, all right? So the F1 score is clearly telling us 0.7 is not a good option for the threshold, okay? So this is the thing. The F1 score takes its lowest values for thresholds with the, let's say, most extreme imbalances between precision and recall. So the F1 score favors threshold where both metrics are either reasonably high at the same time or at least situations where none of them is too low. You know what I mean? So F1 score points to thresholds where either both metrics are quite high or at least to situations where none of them is too low. Okay. Now, in this specific case, we can see that the highest value of the S1 score happens right there, and that will be for threshold 0.3. So in this problem, threshold 0.3 is giving us, let's say the most reasonable compromise between precision and recall. Okay, so for this specific data set, for this algorithm, logistic regression, 0.3 give us the best compromise between precision and recall. And we know that because 0.3 give us the highest F1 score. Okay. All right, guys. So let's summarize the utility of the F1 score. First value of the F1 score. With the F1 score, instead of tracking two separate metrics, at the same time, like the recall and the precision, and trying to balance the value for both, which is kind of mentally loading, right? Guys, the F1 score summarizes both into a single number for each threshold. So the F1 score makes it much easier to identify a reasonable threshold. Okay. Compared to looking at two metrics simultaneously, recall and precision, it's much easier just to look at one value. All we have to do is look for the threshold with the highest F1 score, okay? That's the first advantage. Now, some of you may be saying like, but the arithmetic mean is also a summarizing metric. So the arithmetic mean also gives us that summarizing advantage, right? But remember what I said, the arithmetic mean is more problematic because the F1 score gives us more protection against extreme values from either precision or recall than the arithmetic mean. Okay, so the arithmetic mean leads us to bad options. Okay, so that's why the F1 score it's better than the arithmetic mean. So the F1 score is not only a summarizing metric, but it's a good summarizing metric. Okay, all right, guys. So I hope you learn about um, what recall and precision are. I hope you understood the trade-off between them, and I hope you understood that the F1 score is a metric that we can use to navigate that trade-off and select a good threshold when in case we have unbalanced data sets and we need to find a good threshold. All right, guys. So that's all for this video. Thanks for watching.